Hello everybody. Today on Leetcode, in honor of Thanksgiving, we'll be doing Leetcode Easy Difficulty question number 1640. Check array formation through concatenation. In this video, I'll go through the steps that I took to get to an acceptable solution. Throughout the video, if you feel like my pace is maybe a little bit too slow or too quick, feel free to skip or pause on any of the sections that you need. Let's get right into it. You're given an array of distinct integers R and an array of integer arrays pieces where the integers and pieces are distinct. Your goal is to form R by concatenating the arrays and pieces in any order. However, you're not allowed to reorder the integers in each array pieces I. Return true if it's possible to form the array R from pieces. Otherwise, return false. So the first thing that comes to my mind when I read this question is that this question is very similar to another very common question. Mainly the question being this: given a target string, can I construct that string given a list of substrings? Do you notice the similarities between these two problems? You can just treat each of the list of numbers and pieces as each of the substrings in my list of substrings. My target string will just be this list of integers R. So these two problems are interchangeable, basically. That's what I wanted to say. And okay, before we start doing anything, I think we should take a look at the constraints. So the length of pieces is upper bounded by the length of R, which is upper bounded by 100. The sum of the length of the lists and pieces equate to the length of R. Any list and pieces has length upper bounded by the length of R. The possible numbers that show up in our lists between 1 and 100. Ooh, okay. The integers in R are distinct. The integers in pieces are distinct. So these two facts here, the integers in R and the integers in pieces being distinct, is very useful. Along with this constraint here, that the sum of the length of the lists and pieces is equal to the length of the list R. Without these constraints, this problem by itself will be a little bit harder to do. It's not that difficult, but it won't be as easy as the solution I have in my mind for the problem with these constraints. I'll make a video following up on this that will solve the problem without these constraints, because that solution to that problem is a very good example of showcasing how you could use memorization to solve a problem. Okay, so let's go to the whiteboard and let me explain why these constraints make the problem easier. So let's first copy these constraints, and I'm gonna explain some inferences that one can make from these constraints. Okay, this is not as important. I want to keep these two. Okay. And what are we trying to find? We want to check if it's possible to construct array R from pieces. That is our goal. Again, let's just do this real quick, and so we know what we're trying to do. Okay. So, if we know that the sum of the lists and pieces, they sum up to the length of R, and we're trying to form the array R from lists and pieces, can we say that we have to use essentially all of the lists and pieces once for each list, right? To be able to construct R, I'll have to use all the lists and pieces to do that. I don't believe you can do repeats. Well, there won't be any repeats, basically, because like given in this constraint here, right, it tells us that the integers in R are distinct, so we'll never have to repeat a particular list of integers more than once, right? So let's just write this down. So this implies that we have to use all the lists and pieces, and what this tells us is we will never use a repeat list. We'll never use a list in pieces more than once. So armed with these two facts, we can create a solution in the following manner. So let us say that this is my list of numbers R. Each circle represents an integer between 1 and 100. What I'm going to do is I'm going to look at this first integer here and try to find if there's a list in pieces that start with the same integer. There's going to be two cases. It either there is a list that starts with this integer 2, or there isn't. And like we said earlier, since the integers are distinct, right? If we have a list that has this integer, but it's not in the first position, then we know we can't construct this target string R, right? Since there's no other list in pieces that can possibly have this integer. So, anyways, before we do anything, let me draw my list pieces, and each of these rectangles represents a list in the list of integers pieces. Okay, so what I'm going to do here, like I said earlier, is I'm going to try to find the list of pieces that has the same starting integer. Let's just say it's this one, right? And what I'm going to do now is I'm going to check to see if all the integers to the right of this list matches up with whatever integers in my target array are. So once I do that, if there's any times if there's a mismatch, I know I can't create the final array. Once I do this, again, I do the same thing. Find the list and pieces that has a starting integer of this integer. Do the same thing until we are able to match all the integers in R. Okay, let's try to code this up. So we need a way to efficiently access lists in pieces via their first index. And we know, like I said, from this constraint that all the integers in pieces are distinct. So that also means that all the starting integers in all the lists in pieces are also distinct. So what we can do is we can keep track of a dictionary. Let's call this starting index. What this does is it maps our starting integer to a list of integers. To fill this out, all we have to do is we loop through pieces and simply, what is our key here? Well, it's just the list of the first index in the list, and it should point towards, the entire list. And now all we have to do is we have to loop through our target array R one integer at a time and try to find the corresponding matching lists and pieces. How do we do this? Well, let's keep track of an index. Let's call this cur. And while cur is not equal to the length of R, what we do is we try to find the list and pieces that has that same starting integer. So we check to see if, let's call the starting integer start, and this will be equal to our cur. If start is not in start index, if start is not in start index, then we return false automatically because we know that there's no way of creating that target array R, right? But if there is, now we have to do is we have to loop through the list that has the starting integer and match these integers. So the way we do this is, again, we loop through whatever that list of integers is. So that would be, and we check to see if ARR cur is equal to I. If it is, we continue on. We make sure we check the entire list. Otherwise, we know we can't create the array. So we return false. And after we're done, we will return true because this just means that we never exit out of this while loop early. And it only exits out of the while loop early if we ever come across a case where we can't construct the array R. Okay, let's run the code and see if there's any errors. Okay, it passes for the test case. Let's see if it works for the... Okay, so it works. Perfect. Oh yeah, so let's also analyze the runtime. So what is the runtime here? Well, to construct this list, this dictionary start index, we're looping through pieces, and we know that from the constraints that the length of pieces, number of lists and pieces, is upper bounded by the length of R. And let's just say for now that the length of R is of n. So that means looping through each of the lists and pieces, that takes O of n time. Creating that corresponding entry in the dictionary is still, constant time, so O of n time here. We have this while loop. So what values can cur take? Well, cur can range from 0 all the way to length of R minus 1, right? And we said earlier that R has length n. So this while loop would have O of n iterations. How much work is done in each iteration? Well, checking to see if there's a key in a dictionary, that's O of 1 time. So O of 1 times O of n, we get O of n. In general, this whole algorithm finishes in O of n time. And that's it for today. And as a wise man once said, one Leetcode problem a day keeps unemployment at bay.